discussion was pending in the end. So I will start with that one. We'll just take a relook at this last question that we were doing in the previous lecture. So we were talking about this particular question. Where basically a particle was displacing along this surface in such a way that under the action of such a force that the direction of the force was fixed towards this point, let's say A, but the magnitude was constant. So we saw that situation where if a particle is located at this point, the force acting on it is like this, directed towards the point A, like this. So I told you there are different methods by which we can do this. Whereas if it's at some general point like this over here, the direction of the force is like this. So force of constant magnitude always points towards the point A, okay, and acts in that particular manner on a circular path. So we want to calculate the work done by this force, where F has a constant magnitude, but acts pointing towards the fixed point A over here. Okay, so this was the example. So let's say the initial position of the particle is over here. This is where it is at t equal to 0. And after some time, the particle reaches somewhere here. Let's take a general expression here where this angle is suppose beta. So we want to find the work done by this force from t equal to 0 to t equal to t. So remember, this was the last question we were discussing, and we had seen one of the methods, but that too with a specific numerical value and all that. So I just want to generalize that solution and also discuss how it converges with the other types of methods. Okay. So what we will do here is we will use the geometry of the circle very effectively. So we will see that if we take the general angular position of the particle at any point of time to be like this, if we take that at some time t, the particle's angular position is this theta. Okay. So our theta is changing from 0 to whatever angle alpha at that time t. So this is the angular position of our particle with respect to the origin of the, or with respect to the center of the circular motion, okay, circular track. Okay. at the same time, the force that is acting on it, that is acting along this line here. So that is the chord of this instantaneous point P's chord with respect to this fixed point A. So our force is going to be acting along that one. So it's going to have a magnitude of constant F, but its direction is going to keep varying like this. So this is our force F. Okay. So now we can see that in a small time dt, if it makes a small displacement, if the particle makes a small displacement from here to here, okay, from t equal to t to dt, you can see that our displacement vector will be like this. So that displacement vector will be along the tangent here. So that is making some angle with respect to the force. So in a small time dt, the angular position of the particle will be changing by a small angle d theta, and accordingly the magnitude of the displacement, that will become how much? Okay. So the magnitude of this displacement ds will become capital R d theta, where capital R is the radius of this circle. Okay. So the work done by this force, the differential work done in that time will be F dot ds. So that will become F into R d theta into cos of this angle now. So I'm calling this angle alpha in my diagram, this angle over here. Okay. So as you can see, this angle will be a function of theta. So how it will be a function of theta is that, this is going to be an isosceles triangle. Okay. So this angle is equal to this angle. Okay. So let's say these two angles are gamma each. So gamma is 180 minus theta. Sorry, 90 minus theta. It is 180 degrees minus 90 minus theta. Okay, that is 2 gamma. Okay. Because this angle here is 90 minus theta. So the sum of these two angles, 90 minus theta plus gamma, sum of 3 should be 180. Okay, so gamma from here comes out to be 45 degrees plus theta. Okay. Theta by 2. So this is 90 plus theta, so this comes out to be 45 degrees plus theta by 2. So this angle alpha now therefore is obviously 90 minus gamma, because obviously this whole angle is 90 degrees. It's the tangent with respect to that. So my diagram is not perfect. The tangent is more like this, but anyway, tangent should be a little bit more like this. Yeah, that's better now. Okay, so this angle is 90 here. So anyway, coming back to this, alpha is 90 minus gamma. So that makes it how much? It makes it 45 degrees minus theta by 2. So that is my alpha. So coming back to this now, the differential work done for that small angular displacement d theta with respect to the circle center, that work done will be expressed like this now. Substitute this here. So that will become FR cos of this term, 45 degrees minus theta by 2 into d theta. This will be my actually F dot ds here. That should be like this. So is this all right? Just verify this once. Okay, you can see. So the total work done will be the integrated work done from t equal to 0 to whatever time t. So in that my theta is changing from 0 to some general value which I have taken as beta. In the previous diagram, taken some general value beta at this time t. So I'll get this as a function of that beta only. Okay, so I'll get this as FR cos 45 degrees minus theta by 2 d theta from this to this. Okay, so there are two ways of doing this. You can either substitute this and use it like this, that you know that integration of cos theta is sine theta. Okay, so integration of cos of, let's say, e minus theta d theta will become minus of sine a minus theta plus c. So integration of cos of some constant a minus theta by 2 will become minus 2 sine a minus theta by 2 plus c. You can do this, okay, or you can expand this or whatever, so it doesn't really matter. So this will become fr into minus of 2 sine 45 minus theta by 2, going from theta equal to 0 to theta equal to whatever beta. Okay. So further you can also just write this as this kind of term. So this is the value of f that we'll get. I mean, this is the work done by f that we'll get. So you just check on my integration and calculation and everything once if you like, but seems to be this only. Or I can also do one thing here. Na? We can also write this as fr by root 2, okay, sine theta by 2 plus cos theta by 2. This will become root 2 fr Okay, so that will give you the same thing as this. So number of ways of doing this. Okay, so just make sure all the steps are clear, and also you understood the substitution with respect to the diagram and everything properly. Okay, people, so hope this is clear to all of you. Okay, now the other method that we have discussed now is that we can take an equivalent situation where what we are doing is we can take an equivalent imaginary situation where we have that hemispherical surface and we have just attached a pulley kind of thing here, very small in size. Okay, and there's a thread which is attaching the particle or block or whatever. And on this thread, we are applying a constant force F. So the thread maintains a uniform tension, and the direction of the tension is always directed more or less towards this same kind of point E. So this will also replicate that situation only. Okay, so that T will be equal to F at all times. Okay, and that same kind of thing will happen, that by the time the particle has reached some angular position like this over here, again there is T equal to F acting on it along the chord, whereas its displacement is along the tangent like this. So it's the same situation basically. Again, this angle is alpha whatever. But here what we can do is we can take the thread plus the particle as a system. So on that, the work done by the force F will be equal to the work done by tension on the particle. Okay, whatever work the force F does on the system, that only will be equal to the work done by the tension on the particle. So we can do it that way also. Okay, so that is the advantage of this method. So now what is happening, that going from this situation to a situation where the particle reaches somewhere here, we have to find out how much this point displaces by. So if this end of the thread here is, let's say, the point P. Okay, so we have to basically, so the work done by F will be equal to F into the displacement of that point P. So as we are pulling the thread, that point P is moving from this position to some position like this. So this is the displacement of the point P that we're looking for. Okay, so when our angular position is changing from 0 to some general value of beta, we have to find how much thread has been pulled. Okay, so if this chord length was L1, okay, and this chord length is L2, okay, then we can see that the displacement of the point P is L1 minus L2. Thread length conservation. No? So that all we have to do is geometrically we have to calculate. So L1 we can see in this diagram. This is L1 from here to here, this length. So it is nothing but R root 2. But L2 we have to figure out geometrically how to get the value of L2. So that is nothing but the chord length. L2 is this chord length. When this angle over here has become beta. So when this angle has become beta, this angle, let's say phi, is 90 minus beta. So just drop a perpendicular here. It will bisect this. Okay. So this side is R, this side is R. So if this is X and this is X, bisects this triangle. So we have X is equal to R sine phi by 2. So that is R sine 45 minus beta by 2. So L2 will just become 2x. So that is 2r sine 45 minus beta by 2. So that we can write as 2r into 1 by root 2 sine A sine B. So sorry, sine A cos B, okay, minus cos A sine B. So that is sin beta by 2. हो जाएगा ना इतना? So this L2 should be root 2r into cos beta by 2 minus sin beta by 2. As per my calculation, this is what my L2 is coming out to be, this is what my L1 is coming out to be, and then we'll substitute this here to calculate this work done. And we should be able to show that that work done is the same as what we got in the first case. Hope all of you are understanding this. Please let me know if there's any confusion, any doubt. I made the rough diagrams, but just using that property of isosceles triangle, that one, this triangle over here. This is the chord length L2 which we are trying to calculate, but this side is R, this side is R, and this angle is phi. So we drop a perpendicular here on the chord. So it bisects, it becomes two congruent triangles. Okay, so now we just substitute this over here. So you can see that displacement of that point P is L1 minus L2. So you can take root 2r common and it becomes 1 minus of this cos beta by 2 minus sin beta by 2. So when you multiply this with the force magnitude F now, you will get the same value of work done which we have got from this other method. You can see it's the same term. So you can see that essentially this is a much easier method. We just had to use thread length to just use one formula for the length of the chord. When this angle is beta, we just had to figure out what is the length of this chord. And from the difference in the two chord lengths, we got the work done as that difference multiplied by. So we didn't have to do any integration and all that. So that's why this method is advantageous. Okay, now I'm going to use another method for the same question, which will involve central forces. So before that, I will come back to a bit of practice with central forces because I told you that was important. Okay. So now let's look at another example. Okay. A particle of mass m moves in zero gravity 3D space, three-dimensional space in an XYZ system of coordinates under the action of a force F equal to at position XYZ, where the force is in newtons for XYZ in meters. This kind of function. Now, initially, it is at the point A, 0, 0 and has speed u. So what we want to do here is and after some time it reaches the point, let's say 0, A, A. Okay. So show that force F is conservative and find the work done by F from A to B. If the potential energy for the particle is u naught at A, then derive a general formula for potential energy at a general point x, y, z. Okay. And third thing, show that if the particle displaces under the action of the force F from A, which was small a, 0, 0, to some other point, let's say D, which is A by root 2, A by root 2, 0, its speed at D will be the same as initial speed at E. That is, the speed at the point D should be equal to the speed at the point A. So that you have to prove over here. Okay. So this is a three-dimensional version of a question based on conservative force, which we had discussed earlier. So just try this out. We will discuss in detail, and then we will come back to that question once more, and we'll see another very easy method of solving that. The question with a hemispherical surface and a force of constant magnitude acting towards a fixed point. You will see another very easy method of solving something like that, which will give us a more general method also, that even if it had not been a hemispherical surface and some other coordinates were involved, how we could calculate the work done by the force, etc. We'll discuss about that. So just try this out, people. Okay, anyone got the answer? Kevin, Javal, Ayush, Aman. You must have figured out that it's a central force, right? Yes, Vaishnavi, very good. Okay, so once you figure out it's a central force, it's pretty easy to understand that it is conservative in nature. So you have to just basically develop a formula for it. You know? Okay, very good, Shubham. So can you tell me the work done from A to B? What will be this part? How much it will be? It should come out as some factor into alpha by A, something like this. It should come as numerical factor something into alpha by A. Just try to figure out what that is. So it should be something like this. Alpha is obviously a constant over here. And assume that it's a positive constant, though it can actually be a negative constant also. Okay, so let's figure out the numerical value finally. So we can see that the force being like this, okay. If they make a differential displacement, it will have components dx, dy, and dz. So for a small displacement, the amount of work done by the force will become alpha into x dx plus y dy plus z dz. upon x square plus y square plus z square to the power 3 by 2. So the total work done by this force in any path will be integration f dot ds from whatever initial to final position. So you can see that will be alpha x dx plus y dy plus z dz upon x square plus y square plus z square to the power 3 by 2 from whatever initial to final position. So now we will make use of this. Okay, we will make use of this like this, that let, so you can see that numerator, which is x dx plus y dy plus z dz, is like a derivative of the term x square plus y square plus z square. So if we introduce a substitution that let x square plus y square plus z square is, let's say, some theta square, some, so 2x dx plus 2y dy plus 2z dz is equal to 2 theta d theta, or the numerator that we have over there, x dx plus y dy plus z dz, will just become theta d theta. So we'll substitute these two things here. Substitute. So my integration now will become like this. And then I'll just substitute theta as square root of x square plus y square plus z square. So this will just become alpha into minus of 1 upon square root of x square plus y square plus z square from whatever initial position to whatever final position. So you can see that the quantity we are getting work done finally is a function of initial and final coordinates, and it's independent of path. The integration is showing us that the integration can be calculated without any information about path. Okay, I can go from some initial position to some final position by many different paths, but every time I'll get the work done the same, because it will only depend on the initial coordinates and the final coordinates. The work done by F will depend only on the coordinates. It is path independent. So that is first of all showing you that it's a conservative force. And already by doing this, you have got into that position where we can find out the work done in for any particular change from initial to final coordinates by just substituting the values over here, the initial and final coordinates. So in our particular question, we wanted to find out the work done from the point A to B. So it was this, right? So just substitute the values and you'll get an easy sort of solution for that. Yes, how much is the answer? First one beta, substitute properly Nikita. So देखो A to B के लिए क्या करना है ना, work done from A to B, we have to do this only. You can take the minus sign also outside. Okay. 1 upon root of x square plus y square plus z square from A to B, I mean from the point A, जिसके की coordinates क्या है A, 0, to the point B whose coordinates are 0, A, है ना? So the upper limit will become 1 upon square root of 2a square when you substitute these coordinates, minus the lower limit will become 1 upon square root of a square. To take the minus sign inside, and this will become alpha by a into 1 minus 1 by root. And you can rationalize the denominator and all that if you want, but you can just leave it like this. So this is approximately alpha by a into 1 minus 0.7 or approximately 0.3 times alpha by a. Because you can always take root 2, or rather you can always take 1 by root 2 as root 2 by 2, which is approximately 1.4 by 2, or approximately 0.7. You can always do this type of calculation. Yes, Vaishnavi, that's correct. Take LCM and do it that way also. Okay, so that's done. Two things are done. We have shown that it's conservative, and we have shown that work done for this particular case A to B is this much. Okay, people. So are we all clear with this part? I hope no doubts. Yeah. Now the next thing is that once we have shown that the force is conservative, we can define potential energy. We can define potential energy by this relation that delta U is negative of work done by the internal conservative force. So in this case, we will define delta U is negative of the work done by that force. So final potential energy minus initial potential energy should be negative of that, you know, alpha by A. Sorry, what was it? It was alpha into that whole equation minus of alpha upon square root of x square plus y square plus z square. And there was another minus sign here going from initial to final. So that we can now write as alpha into 1 upon square root of final square minus initial. For any two general points, we can write an equation like this. Okay. Now it is given to us that potential energy at the point A is equal to U naught, okay, where A is having the coordinates A, 0, 0. So potential energy at the point P we have to find out, where the point P is having coordinates X, Y, Z. Okay, so take this as a final point and take this as an initial point. Okay. So the general expression for potential energy will become like this: alpha into minus 1 by A. So our general formula for potential energy as per what was given to us is that potential energy at the general point P will become alpha upon root of x square plus y square plus z square minus alpha by A plus U naught. That will become our expression of potential energy. Okay, and then we can in general say that only internal conservative force is acting on the particle. So mechanical energy, I mean, change in kinetic energy plus change in potential energy should be zero, because work done by external force is not there, work done by non-conservative force is not there. So we have this. Yeah. So if at the point A, the speed of the particle is VA, then and at the point C or D or whatever, the speed of the particle is VD, then we can show that okay. So we'll have half m Vd square minus Va square, okay, plus you can see, no, this is the formula for delta U. So potential energy at D minus potential energy at A should be zero. So now we'll just use this formula for the change in potential energy. Now we won't use the expression of potential energy. We'll use the expression for delta U. So we'll substitute that here. So this will become half m. Sorry, this was A by root 2. Let's take you back to the question. Yeah, so see, the point D was this. So we have to show that these speeds are the same, whereas the point A was this. Plus alpha into, now this will become the final coordinates substituted there. So square root of A by root 2 square plus A by root 2 square plus 0 minus the initial coordinates substituted in that. So the initial coordinates were A 0 and 0. Okay. So this total thing should be 0. Change in kinetic energy plus change in potential energy should be 0. That is this. Okay. So half m Vd square minus Va square plus alpha. Now you see this is the same thing. This is 1 by A square by 2 plus A square by 2. So that's A square. So that's A. And this is also 1 by A. So this term becomes 0. So that's how we now get that Vd square is equal to Va square. And that's just the speed. There's no question of plus minus. So Vd must be equal to V. So it just so happens that if you go from this point A, which was A comma 0 comma 0 to this point D, which is A by root 2 comma A by root 2 comma 0. It just so happens that A to D, your delta U is 0. So therefore, change in kinetic energy should also be 0. So therefore, the speed should be the same. Okay, so that is the final conclusion that you can see. Okay, very good. So hope this is clear to all of you. Now let's come back to that particular question earlier. So what we were discussing about now earlier is central forces. Remember, we had talked about central forces, and we had seen that in general a central force is given by an expression like this, that it is some constant, let's say alpha or c or whatever, upon some kind of relationship as a power of the distance with respect to the central point to which the force relates. Okay, so there is some kind of a central point which we take as the origin. Then on the particle located at any point which is at a position vector r, okay, the force acts with relation to r cap, and its magnitude is related to r. So if alpha is positive, then the direction of the force will always be like this. If alpha is negative, it will be towards the point. Okay, so if this particle now moves from here to some other position now here, so now again this will go to position r prime, so the force will be like this now, and the magnitude of the force will be proportionate to that power of this kind of thing is called a central force. And we had seen that central forces are conservative and all that. Okay, so we had seen that you know, work done by central forces can be shown to be path independent, so they are conservative, all that. So the earlier example that we had taken now, where the force was just now alpha xi cap plus yj cap plus zk cap divided by x square plus y square plus z square to the power 3 by 2. Again, this is nothing but alpha r vector divided by r cube. So it is alpha by r square r cap. It's like that, because position vector in 3D is this, and the distance of the point is nothing but this, the magnitude of the position vector. So you can see that this actually relates to this central force. So the moment you get that relation, we could have done this much more simply by using this. So now we could have said that, okay, the work done by this force, which is integration f dot ds, is just integration of alpha by r square r cap dot ds, which I taught you is simply this, because r cap is a unit vector, so its dot product with this is nothing but this, is the magnet, is the component of ds along that r cap. Okay, so for example here, if the particle is making a displacement ds like this, then r cap dot ds is nothing but the component of that along r cap. So it's nothing but this one, dr. So r cap dot ds is nothing but ds cos theta in that diagram, that is nothing but dr. So next step, from whatever initial to final, this just becomes minus alpha by r from initial to final, and then you just go back to that. Now this is minus alpha upon r is nothing but root of x square plus y square plus z square. So we could have avoided some work if we had used this. This would have become our expression for work directly. Okay, and then delta u is negative of work and all that. So basically what happens is you can convert from xyz to r and r cap, okay, by using this relation, that vector position is given by xi cap plus yj cap plus zk cap, and magnitude of the vector position is this, and of course r cap is nothing but vector r divided by its own magnitude. So we made use of that also. Okay. So this came under the category of central forces. Okay. So likewise now, this other question that we had, we could use this there also. Just share with you quickly how we could have used that. So what is happening in this case is, when the particle is at a general point like this, we saw that the force acting on it was towards this point now. So this point only we will take as our origin. Okay. So the force vector, which is acting like this of constant magnitude but direction towards this, is a central force. because with respect to this origin, you can see that the position vector of this particle is nothing but this chord. Okay. This only is the r vector, and this is r cap. Okay. So when we said that the force is constant in magnitude, but points towards the origin, we can say that F is equal to minus F r cap. So it is basically negative of F as a constant upon r to the power 0 r cap. Okay. So it is a central force with the value of capital N as 0. And 0 is also a real number, so there's no problem with that. So therefore, it had to be conservative. Okay. And we could use the mathematics of central forces now to calculate the work done. So that was the third method I was telling you about. Okay. So before I proceed with this, Rakshit, I will just give you time to take down this part. And now this method only that I've used over here, इसमें क्या हो रहा था, n का value, it was a central force with the value of n equal to 2. Now in the lower example, we just take the value of n as 0 and proceed the same way. So it's actually even easier because the value of n is 0. Yes, Nikita, I'll come back to that. Okay, let people just finish writing this down and just go through this once more. Then I'll show you how the last one is also, the second one is also a central force, because its direction is always pointing towards a central point. No? Its direction is always pointing towards a fixed point. So it's a central force and its magnitude is constant. But remember, constant is also a function. No? Constant function bhi to function hota hai. It's like that, you know. If I say you have a general polynomial x to the power n like that, but n can be 0 also. No? So in that case, it's not a function anymore. It becomes a constant. So you can say constant function is a special case of functions. No? So that's how this is becoming a central force. So because I can express this force now in this manner, it is some constant. This force F is some constant, which is actually minus F divided by r to the power 0 r cap. Okay. And that constant is a negative value. So it's pointing towards this. It's pointing towards the point O rather than away from the point. Is it clear now, Nikita? Okay. So now see, it becomes very simple. So work done by this force, now we can just go with that polar method using r and r cap. Integration f dot ds. Yes, हो जाएगा. Minus f r cap dot ds. So that is minus f can come outside and r cap dot ds is just dr. Okay. Okay. You can just use this. So it's just becoming, the work done by the force is just becoming minus f into r final minus r initial. Where what is r final and r initial? R final is the distance from that point O or A, whatever, finally. Okay. And R initial is the distance initially. Okay. So again, in our example, now this point is becoming O or A or whatever. Okay. So this was our initial position. This was where it was at t equal to 0. So this is our R initial. Okay. So our R initial would have been R root 2. And then this is where it was at some time t. So this is our final position. Okay. And then we just had to calculate that. So that we had got from the chord. So R final kitna tha? It was equal to 2 times R sine of 90 minus beta by 2. So that kind of thing from that triangle. Okay, so it's that same thing all over again. So this is my R final and this is my R initial, and you can see that the work done is minus F into R final minus R initial, or I can just write that as F into R initial minus R final, and just substitute these two values, the initial value and the final value. That's it, we'll get the answer. So that's another way of looking at this problem and understanding it, that if I have a constant magnitude force also, but it's always pointing towards a fixed point or pointing radially away from the fixed point, that is also a category of central force. And any central force will be conservative, and the expression of work done will always depend on the final distance and the initial distance. It will depend on R final and R initial. How it depends, that depends on the power factor n. When the power factor n was 2, it depends on 1 by R. But here the power factor was 0, so it depends directly on R to the power 1. R doesn't come in the denominator, R comes in the numerator. You know, also wanted to discuss some questions related to power in work by energy. So let's look at that next. We have looked at a lot of applications of virtual power methods, so you're good at those things. But let's just look at direct problems based on power. So we have a particle in 1D motion under the action of a force such that the power delivered by this force, okay, by this force, by power we mean instantaneous power, okay, that power is equal to C into square root T, okay, and mass of the particle is M. So first of all, find F, the force, as a function of time. Okay. And assuming u is 0 at t equal to 0, find its velocity as a function of time. Just try this out. It's a pretty simple, straightforward situation. Just work this out. Yeah, anybody got the answer? Getting this relation? Let's check out. So see, how do we define the instantaneous power in 1D motion? Power in general is the dot product of force and velocity. So in 1D motion, if the instantaneous force is F, the net force that is. Okay. So here, F into V will become equal to C root 2. Okay. Now this is 1D motion under the action of the single force F. Okay. So that F is actually equal to ma. That is m dv by dt. So next, we'll substitute m dv by dt into V is C root T. So that is how we will get all this. So first of all, force as a function of time. So aa jayega. From here, the first part, force as a function of time will become C root T by V. But we need to find out V as a function of time. So that for that we will use this one. So from this we will get mv dv is equal to C root T dt. Okay, so we'll integrate this. Now t equal to 0, it's told to us that u was 0. Okay. So half mv square will become like this. So further our v will become square root of 4 by 3 c by m t to the power 3 by. So therefore our force So we wanted to find out f as a function of time. We wanted to find out v as a function of time. V as a function of time we've already got. Okay. Oh wait a minute, I made some mistake now. This is square root. So this will be a different power. It will be half minus 3 by 4. No? That will be minus 1 by 4. Okay. So ultimately you can see that v is proportional to t to the power 3 by 4. Okay. And that's why your acceleration becomes proportional to derivative of this. So that's t to the power minus 1 by 4. Okay. So power. So I mean that's why force is also proportional to this, and power is proportional to the product of V and A. So it becomes proportional to the power. Okay. Rest are just the constants. So hope this was clear, people. So Amog, hope this is clear now. Okay. Okay, another type of question where you have to relate power sometimes is in a circular motion situation. So a particle starts from rest, okay, on a circular path at, sorry, of radius r. Okay. If the kinetic energy of the particle is equal to c into t, where c is a constant, okay, at time t, okay, and mass of the particle is m, then find the magnitude of its acceleration at t equal to t. Okay. The net work done by forces, okay, the instantaneous power as a function of time. Okay. The instantaneous power by the net force acting on it as a function of time. We have to calculate this. Just work this out, people. Yeah, anybody got the answer for this? Just use the basics of circular motion along with work energy over here. So let's say the particle is starting from rest somewhere here at t equal to 0. By the time it reaches here at time t, it's got some angular displacement theta, it's got some velocity v like this. So the kinetic energy half mv square, that is equal to how much now? That is equal to linear function of time ct, where c is some constant. Okay. Now you also know that the net acceleration at this point of time, it will be the vector sum of centripetal acceleration and tangential acceleration, where tangential acceleration will be rate of change of speed and centripetal acceleration will be equal to v square by r in magnitude, where r is the radius. So this first equation, what it's showing us, you can see that speed as a function of time is square root of 2c by m t. So speed is proportional to root t. You can see speed is proportional to root t. So what that tells you, that the tangential acceleration that will be proportional to 1 by root 2. Okay, Jabin. So I'll just verify your answer. So the magnitude of the acceleration at the time t, we have to use like this. So you can see the centripetal acceleration v square by r will become such that from this kinetic energy, or from equation 1 you can see v square will become 2ct by mr like this. This is your centripetal acceleration. And just now we saw that the tangential acceleration is, we can write this now as square root of c by 2m like this, is a constant. So this and this will combine here. So it's this sort of a function. Yeah, that's okay. I understood. Okay. So you got the tangential acceleration. Now you have to also figure out the centripetal acceleration, which you're getting from here. Okay. Now the B part is obvious. The work done is going to be the change in kinetic energy. So that is nothing but just CT. So that B part is obvious. Okay. But C part, the power will be the rate of this work done. So it will be rate at which the kinetic energy is changing. Okay. So that power you can see will over here become C. It will have a constant power. Or you can also understand this way that power is equal to F dot V. So that will become actually tangential component of force into velocity. So that will become mass into tangential acceleration into magnitude of velocity. So tangential acceleration into magnitude of velocity you can see over here when you see the product of these two. Into the instantaneous velocity is this thing. Just yeah. So you see all this stuff cancels out and we are left with just C. So two ways you can go about the net power. It is rate of change of work done, and the work done is the kinetic energy itself. That's why I gave you this in succession one after the other. That is the simplest way to understand. Your kinetic energy is increasing linearly with time. That means the rate of change of kinetic energy is constant. So that means the net power delivered by the force, I mean the net power delivered by net force, that has to be a constant over here. And the other is the more complicated way of understanding it is as F dot V. So in circular motion, when you take F dot B, velocity is along the tangential direction. So the dot product with force becomes the tangential component of force multiplied by velocity. So tangential component of force is nothing but mass into tangential acceleration. So hope this question is also clear to all of you. Okay. Now we'll go back to an interesting example which has to do with the spring mass type of systems, which are the most common examples in application of work energy in this particular chapter. So what is happening is we have a combination of two blocks and they are lying on a rough surface. So this has a coefficient of friction mu. This block is M1, this block is M2, and they are connected by a spring. So initially, both blocks are at rest, okay, and the spring is relaxed. Okay. Now, a constant horizontal force F is used to pull the block M2, okay, as shown. So we start applying a force horizontally like this. So assume F is obviously greater than mu M2G. So the block starts to move. Okay. So first of all, find M2's speed V2 as a function of X, the extension of the spring, okay, if M1 does not move. Okay, due to friction, M1 does not move. That's the easy part. Now the second part we just have to find out the minimum value, the minimum magnitude of F needed so that M1 should be disturbed from equilibrium. We want that M1 should not remain stationary, it should get disturbed from equilibrium. And what is the minimum value of the magnitude of the force we require? You should get all your answers in terms of the quantities given. So both the answers will be in terms of M1, M2, K, G and mu, in terms of these parameters. Just try this out, people. Anybody got the answer for the first part? If you're taking a situation where you assume that the first block has not yet moved, then it's a very simple case of just, so starting from this position, x equal to 0, u equal to 0 on the rough surface. Now, after some time, if m1 has not moved, but the spring has got extended by x, because this force was greater than the limiting friction. So you can see that this block here has got displaced by how much? It's got displaced by x. Okay, and along with this force, there is mg normal reaction, kinetic friction, spring force, all this acting here. Okay, here there will be some kind of static friction because this block is at rest. So that is the idea. So we can solve this in many ways. We can take, for example, you can take the blocks plus spring as a system. So we can say that work done by the external force plus work done by friction is change in kinetic energy plus change in potential energy. Okay. So this is the external force thing. This is the non-conservative thing. So here, this will be Fx minus mu m2gx will be equal to half mv square, or rather m2v square plus half kx square, because by now the block has developed a speed v. So the speed of this one v2 or whatever, so this is v2. So from this you can see that the kinetic energy of this block, half m2 v2 square, is equal to a quadratic function of x. So its speed is like this, the square root of 2 by m2 this kind of. This is v as a function of x. Everything inside the square root other than x is a known constant, m1, m2, mu, g, all this, whereas x is the variable. So you got this v2 as a function of x. That was the first part. Okay. Now I want you to find the condition on f. What is the minimum value of f so that the block m1 gets disturbed? Center of mass usually not really help us here, because center of mass, by that you can either find the acceleration of the center of mass or velocity of the center of mass, but you still have to use work energy, or otherwise you will end up doing like this, that you will calculate the acceleration as a function of x and then integrate that acceleration to find v. So that is like deriving the work energy equation. When you find acceleration as a function of position or displacement and you integrate it, you ultimately end up deriving the work kinetic energy theorem. You have F is equal to ma. If you take dot product with ds on both sides and integrate it, you get nothing but net work done on the left hand side, and that becomes change in kinetic energy on the right hand side. So you can do it, but it will not really help. Okay. The convenient thing here is to use work energy. Okay, anybody got the answer for the second part yet? In the second part, now what you have to understand is that if you look at the free body diagram of the block M1 at any point of time, when it is not yet moved, so its speed is 0. So there's static friction acting on it, its acceleration is 0. But if Kx becomes equal to mu M1g, okay, now the block M1 will just start to get disturbed from equilibrium because the spring force has reached, okay, as long as static friction is less than the maximum value, it's fine, acceleration will be 0. But the moment it reaches the limiting value, okay, so basically the condition for M1 to move is that x should be greater than equal to mu M1g by k. Okay, just about equality is also fine. This is our first thing. Okay, and on the other hand, we had the equation that half m2 v2 square, you remember, was f minus mu m2g into x minus half k square. This was the other equation that we had. So from this you will see that what is the maximum value of x possible. Okay, the maximum value of x possible is when v2 becomes 0. When the kinetic energy of this block becomes 0, then x reaches its maximum value. Because you can see that this kinetic energy of the second block as a function of x is a quadratic function like this. And this is like some alpha x minus beta x square, this kind of one. So it reaches the maximum value when the block comes to rest again. Okay, so x reaches the maximum value when v2 is 0. So यहाँ से x का maximum value कैसे निकालेंगे? When this becomes 0, that means the kinetic energy of that block 2, when that becomes 0, x has become x maximum. Okay. So you'll see that that happens when either x is 0, which is obviously not the case, or x is 2 times f minus mu m2g divided by k. So this is the maximum value. This is the x maximum. Okay, assuming that this block is not moved. So now the limiting condition becomes that when the spring has reached maximum extension, okay, but still it has not been able to displace this block. Now just at that moment, if the block is ready to get displaced, that means you reach the limiting condition for the block M1 to get displaced. Okay, that's the idea now. So just at the moment when the spring reaches the maximum extension because of the force acting on the block M2, if M1 is ready to be displaced at that instant, that means you're getting the limiting condition for M1 to get displaced. Okay. So combining this and this, the condition for M1 to just have a tendency to displace. A limiting condition is that X maximum should become equal to this value here, mu M1G divided by K. So in other words, 2 times F minus mu M2G by K should be equal to mu M1G by K. So you will get F should be equal to mu G, if you take common, M1 by 2 plus M2. Very interesting result like this. Sometimes students tend to make the mistake of taking the maximum extension at the equilibrium point for this block when acceleration should be zero. That's not the case. The maximum extension is when the block M2 reaches the zero kinetic energy state, not the equilibrium state. So this is that limiting value of F. So we know that if the force is greater than this F that we've got here, then M1 will start to move. It will develop kinetic energy. But if F is less than this value, then M1 will not move. If it is exactly equal, it's just about ready to move at that position. So hope this is clear to all of you people. Okay, with this we'll conclude today's session. Best of luck for the test coming up on Sunday. Work energy is going to be an important part of that. Okay, so make sure you revise everything properly. And next week onwards, we will start with heat and thermodynamics. I have already sent you the module PDF. I'm sure most of you have the hard copy or the paper copy of the module also. So you can start working on that after you finish the test. We will start according to zeroth law of thermodynamics and thermal expansion. So you can start preparing yourself and also conclude everything in work energy. That's it for today, people. Wish you all the best.